Okay, so I'm recording now. Section 3.2 is where we left off. I'm excited for this, as I was just saying before I hit record, because percentage preparations is basically chemistry, which is exciting for me with a chemistry background, but should be exciting for you a little bit because you guys did all of this in chemistry 1120. Now we're going to make it a little bit more math related than chemistry related, but this is for most of you who can remember 1120 review. Well, I mean, even if you can't remember 1120, you've seen this before. Very exciting, very straightforward stuff. And again, this is section 3.2. We haven't actually done any new math since Tuesday last week, so it's been a while. On Wednesday we did review, and on Thursday you had your tests. So last week, if you can remember, we were doing percentage problems, and we looked at page 11, page 12. So let's look at this percentage preparations. It is literally concentration. Just because I'm a chemistry teacher a lot, many semesters, and because you guys have done chemistry, I just want to remind you what a concentration is. A concentration is the amount of something in a certain volume, or it could be actually in weight. It's typically the solvent in the total amount. Okay, so examples, you could dissolve a tablespoon of sugar into a cup of water. So the sugar would be your kind of the chemical we're interested in, and the cup of water would be the solution. And in chemistry, we typically would use mole per liter. Luckily for you guys, we're not dealing with moles in math. We're going to deal with these concentrations as percentages. The percentages could be in three ways. They could be calculated in three ways. We could measure the volume of the, now see, this is where it gets different than chemistry. And pharmacy or medicine might call it the drug, or they might call it the constituent. So in the first type of percentage, we're going to look at the volume of constituent. Again, think of like the medicine. It could be a cough syrup diluted. It could be, paracetamol. I'm just naming, I don't know many drug names, but it could be the drug itself in milliliters mixed into a certain amount of solution. Typically, the solution would be like some sort of water or syrup, or sometimes they use different alcohols. It's the first type of percent is the volume of the chemical we're looking at, in your case, the medicine, over the volume of the solution. The solution is kind of like your total amount of the liquid at the end. We could also calculate percentages using weight, and this is very useful for solid ingredients. So you could be mixing a solid powder into a solution. Sometimes you could be mixing a solid powder or something into an ointment, which you could easily weigh. So there's volume and volume, there's weight and volume, and then there's weight over volume. And each of these percentages are basically done the same. It's just what type of chemicals are you using? What type of medicine? If the medicine is a liquid, you might measure milliliters. If the medicine is a solid, you might weigh it by grams. Okay, so let's look at this. Might as well get started. Oh, and one thing I'll mention too is, because we're dealing with percentage problems, you'll notice that typically we're using 100 milliliters or 100 grams of the solution, of the mixture, you could say. Solution, you could say the mixture, same kind of thing. So I hope this is bringing back some memories for some of you, but if it's not, who cares? Because we're going to do it together. Now, these formulas are given. So you don't have to memorize these formulas. And the first one we're going to look at is volume. So the formula for this, well, let me read the beginning here. It says when two liquids are mixed together, the active ingredient, see, now we're talking chemistry, we call it the solute. And then what it's mixed with is called the solvent. So for medicines, it can be quite complicated. In chemistry, you might use a solid and then water. But in medicine, your liquid ingredient, your solvent could be, flavorings like corn syrup or like a syrup, a water and sugar solution. Doesn't really matter. We're going to take a solute, mix it together with a solvent, and together it makes the solution. And that's really important. It's always the amount of the active ingredient, the solute, over the entire solution. Again, it's always over the total. Excuse me. To turn it into a percentage, we then multiply it by 100. Okay. So let's have a look at some of these examples. Example number 1. Find the concentration, and it's so V over V means volume over volume. Oh, hold on. Sorry, I just yawned. I find Sundays I'm always tired, and I just had a 2-hour class, so just kind of used all my teaching energy just then. V over V means volume over volume. So milliliter over milliliter, or liter over liter, whatever. It's volumes. So we're going to mix 20 milliliters of glycerin, dissolve it in 60 milliliters of liquid. Now, you really need to think about what you're doing. You're taking 20 milliliters of glycerin. You're going to mix it in 60 milliliters of another liquid, like this could be anything. And we're trying to find the percent concentration of that active ingredient, that glycerin. So this would be my solute, but my solution, change my color here, would be everything. So it would be the total. I didn't really draw my picture with enough room. This would be the solution. SOLN. SOLN. We typically, chemist people or sciencey people would call this a solution. Okay. So pretty straightforward. The percent concentration is 20 milliliters. That's my solute over the total amount of the solution. So 20 divided by 80, right? You would get if you did this, 20 divided by 80. If you did this on your calculator, it would give you 1 over 4 or 0.25, and then you multiply it by 100 to get the percent. So this chemical is 25%. This mixture is 25% glycerin. All right, let's look at some examples. This is pretty easy. Oh, well, of course, example number 2, they switch it around a little bit. Okay. How many milliliters of liquid phenol should be used to make 240 milliliters of calamine lotion? Now, we're making this. This is my solution. This is my total. Okay, we're making 240 milliliters. So we use the formula from above. My percent concentration is equal to my solute over my solution. And I'm going to enter my numbers here. I'm going to fill in my numbers. Now, one thing you want to be careful with is when I'm doing an example like example number 2, I know that, let me pick another color. I know that my solution is 240. I know that my concentration is 2.5%. But whenever you do, and this is review from the previous section, whenever you use a percentage, you change it to a decimal. So first things first, I'm going to change that to a decimal. So what this ends up being is 0.025 equals X, what I'm looking for, over 240 milliliters. Or you can just say 240. You don't need the milliliters there. So that means X will be 0.025 times 240, and we will get our answer. So decimal 0.025 times 240. 6 milliliters. Now, how do I know it's milliliters? Because this is milliliters. They must share the same unit. So if this was liters or pints or quarts, my answer would be in liters, pints, or quarts. All right, you guys did really good on the unit conversions, by the way. I was a little nervous, but you guys did very well. All right. Sorry, just want to see how many examples there are. There's a lot. Wow. Oh no, never mind. I was going to say there's a lot, and then, yeah, anyway, sorry. I'm just talking to myself. We're not going to do all of these, but let me do another one in the middle here, and then I'll get you guys to try a couple. So, okay, so, oh, no, well, that's kind of similar. These are all pretty straightforward. I'm trying to see, what would be useful for me to do. 5. Okay. Let me do one more, and then let me do one up above, and then I'll get into example 9 and 10, because something, especially number 9, what you'll notice with number 9 is we have liters and then we have gallons. So let me come back to those. Let me just do one more. Let me try. All right, I'll try 6. Why not? I'm just going to pick one. I'll try 6. So 6, example number 6, 30% solution of dimethyl sulfoxide is what we're making. How many milliliters can be made if we're using 420 milliliters of pure dimethyl sulfoxide? Now, I'm going to go a little further with this one, but to get this set up, it's actually pretty straightforward. So we can use my formula. The percent concentration is my solute over my solution. It is times 100%, but you'll notice what I'm going to do is I'm going to change the 0.30, I'm going to change 30% to 0.3. My solute is 420 milliliters. You don't need the milliliters. You can add that in after. And I'm looking for X. Okay, so what that ends up being is X will equal to 420 divided by 0.30. And that's it. Pretty straightforward. But there is one thing I want to mention to you. So this will make 1,400 milliliters. Now, I'm going to add something to this. You're done. This is your answer, okay? Halas finished for 1,400 milliliters. However, if this question said, how many milliliters of solvent would you add? Like, what I mean is, how many milliliters would I add to make this solution? So this is just a bonus. Well, 1,400 minus the 420 would give me 980. This is how much solvent was needed. This is not in the question, okay? But there might be a question like this in the notes somewhere. I'm just guessing because this is something we typically would talk about in chemistry. How much water would you need to add, or how much solvent would you need to add? Well, my solute is 420. My solution total is 1,400. So I would need to add 980 to make this. That's not part of this question. Okay, so Abdullah asked a really good question. why aren't we multiplying it by 100? Well, okay, maybe I've kind of set this up a little bit confusing. I'm setting this up how we would have looked at a percent problem in question 3. So like Abdullah's question is, okay, well, let's look at number 7. I can explain where is that 100% going? Well, watch this. And this, Abdullah, and for everybody in this class, this might make a bit more sense for you. Watch this. Okay, so my formula is percent of the, concentration. Oh, are they calling it concentration? They're probably not. Oh, they are. Okay, they're calling it concentration. That's good. Sometimes, when I'm teaching, I forget if I'm in chemistry or math class. So the percent concentration is your amount of solute over the amount of solution times 100%. I'm writing a little small here because I'm going to show you what I did with that 100%. Okay, so 0.2% equals, well, this is my solute, so 12.5 over x, and then times the 100. But what I do is when I change this to a decimal, I'm getting rid of that 100%. So really what I'm saying is I would have 0.2 over that 100. That's where the 100% goes, equals 12.5 over x. So 0.002 equals 12.5 over x. And you get the idea, and we can solve this. Oops, sorry. I'm going too fast, over x. So you can solve this for x. This would be 12.5 over 0.002, and we would get our answer. So that's where that 100% goes. The 100% is what I'm using to change this into a decimal. So 12.5 divided by this number, and I'd get big number here, 6,250 milliliters. We will prepare 6.2 liters or 6,250 milliliters. Thank you. Thank you, Abdullah. That was a good question, actually. And, I kind of felt bad because I didn't mention this. I just used this to turn this into a decimal. Sorry. Sometimes, I get so comfortable. I'm just like, oh, they know this. And I'm sure you did know that, but it was a very good question. Okay. I'm going to zoom out here. I know that this is a little hard to read. This is about as big as I can make my screen. Maybe. Okay, here we go. Let's try one more. Yeah, you guys can see that. So why don't you give these a try? Very easy. You can put your answers in the chat for examples 3, 4, and 5. And if you need the formula, again, the percent concentration is the amount of solute over solvent times 100. Oh, not solvent. Oh my gosh, going too fast here. Solution times 100. A little hint here is the solution is your solute plus your solvent. Okay, I'll stop talking. Actually, let me check the chat first. Okay, before I do example 3 and 4 and 5, and you guys can keep going if you know. There's a really good question in the chat from Lola. I think I'm saying Lolo. I don't know if I'm saying your name right. How do you know the difference between solute and solution? Solute is always kind of your medical ingredient you're using. A good answer to that is the solute is the smaller amount. So it's typically your medicinal ingredient or your active ingredient. You guys might talk about in other courses, the active ingredient. So the solute is your smaller amount. It's your medicine or it's your active ingredient. The solvent is everything else. And together, they make a solution. So the solute is your medicine, your active ingredient. It's the smaller chemical. The solvent is like the liquid that you would add to make it. And then together it makes the solution. So it's like if you had tea and water, or well, okay, basically if you were making a drink like a tea or a coffee, the tea, like the tea leaves or the tea bag, would be your solvent, or sorry, solute. Your water would be your solvent, and the drink itself is your solution. That has nothing to do with example 4, by the way. But anyways, so there you go. Okay, I'm going to stop talking. I'll give you a couple minutes to try these. I am going to erase this tea part just so you guys can read the questions. I'll be back in 5 minutes. We'll look at the answers. All right, I'm getting lots of answers in the chat there. Oh man, lots. People are solving number 1, 3, 4, 5, everything. This is great. Okay, just kind of finish up whatever you're working on. One more minute at 12:10. We will look at these answers. All right, one more minute. Okay, let's have a look here. Oh, more questions or more answers. All right, cool. I'm getting so many answers. That's excellent. This is pretty easy. Like think it now. Just take a second and think about the crazy stuff we did in chapter like 1 and 2, and then think about something like this. Pretty straightforward, which is good. So I'm going to quickly go through the answers here. Then I'll show you one where we might need to convert a unit, and we'll go into another topic. All right, so let's quickly get these done. Number 3. So we're making 250 milliliters of a lotion. So this is my solution, right? This is what I'm making. And we're using 4 milliliters of liquefied phenol. So I'm looking for my percent concentration. Very easy. It's going to be 4 over 250, and I'm going to multiply my answer over 100. Very straightforward. So I would get, I got 1.6. Is that what you guys got? Let me check the chat. Yeah. Oh, a lot of people are getting 1.57. Did I get 1.57? 4 divided by 250. I didn't get 1.57, but I did get 1.6. I don't know where the 5.7s are coming from, but it's 1.6%. In preparing, yeah, no, that's right. Okay, I'm just seeing if I made a mistake there. No, if any of you like subtracted 250 minus 4, you don't need to, because the 250 is the final amount of that lotion. So don't subtract the 4 from 250. We're making a total of 250 milliliters of a lotion, and we're using 4 milliliters of phenol. So if any of you on the bottom here use like 244, you did not need to do that. Okay. You would use 240, or if somebody down here said 246, that's how much solvent you're adding. Let me check the chat before I move on. Yeah, okay. Or sorry, so some people were like writing 254. You didn't need to do that here because this is your total amount. So if anybody with the 1.57, if you added them together, I know what you're thinking, but not for this question. We're making a total of 250 mils of the lotion. Just be careful with the kind of way that the question is worded. But for the people who did add, like you were thinking very good, just be careful with the question. If this question said, to make this solution, we took 250 milliliters of a lotion and then mixed it with an extra, 4 milliliters of the phenol, yes, you would add them together. But the 250 is our total solution. I hope that makes sense because I can see where some people added. All right, number 4. What is the percentage strength of a solution with 100 milliliters of ingredient in enough water to make 4,000 of solution? So same thing, right? This is a solution. So the percentage of my concentration is 1,000 over 4,000 times 100. That's it. So this would be 25%. Right, this is pretty easy. All right, number 5. Peppermint spirit contains 10% volume, V over V, which means volume over the total volume of peppermint oil. What volume of the spirit will contain 75 milliliters of the oil? So we're trying to find the volume of the solution. This is, again, worded, be careful with the wording. We're looking for what volume of this solution, this final solution, will contain 75 milliliters of the oil. Okay, so 10% is going to equal 75 milliliters over X. And then, of course, it is times the 100%. So what you would get is you would get 0.10 equals 75 over X. X, I love this, that I have enough room to write here. X will be 75 over 0.10, and you'll get your answer. 750. Now that's of total solution, right? So if the question was how much solute would you add? In this case, the solute is typically, like when you see the word spirit, it typically means some sort of alcohol. You would subtract. So this would be what, 675 milliliters were added, but that's not what the question is asking. Okay, I hope that makes sense. Let's go down. Let's look at let's see what 8 is. Yeah, 8's the same thing as before. Let's look at number 9. Now, hold on. I got to grab something for number 9. Be right back. All right, coming back. Hold on. I have with me. I took a copy of your formula sheet when you guys did your test on Thursday. So I had all the unit conversions handy. The problem with this question is that the liters and gallons are not the same. They have to be the same unit. Have you ever heard the phrase in English, people say, oh, it's like apples and oranges? You can't compare liters to gallons. One is a metric unit and one is an imperial unit. Just for the record, and I mentioned this when you guys were doing your test, if it just says gallons, we're going to use American or US gallons. And this is in your data sheet, your formula sheet. So a lotion contains 15% by volume glycerin. How many liters of glycerin should be used to make 5 gallons of the lotion? Okay, so a couple things. 5 gallons, we need to convert that to liters. You could convert the liters to gallons. Like I could change this to gallons, but that's not really how we work in the rest of the world, right? If you're not in America, you probably use liters. So I'm going to change the gallons to liters. And I know that, let's see if it's here in my sheet. Yes, 1 US gallon is equal to 3.785 liters. Now, this answer that I'm getting, and you guys know this, I know you know this because so many of you did this on your test. It was perfect. This would be 18.925 liters. This is my solution. Okay, every question is basically giving you the solution. So now 15% equals X over 18.925 times 100. I don't know why I wrote so big. So 0.15 is X over 18.925. X would be these guys multiplied together. Sorry for my writing there. Wow, that's messy. I think I'm trying to write too quick. 18.925. And I would get 2.84 liters, we'll say. You could say 2.8 liters. I mean, you could say 3 liters. I probably wouldn't say 3 liters though. In a real, if you were doing this at work, the difference between 2.8 liters and 3 liters is almost a cup if you think of measuring. I mean, it's a lot of liquid. So I wouldn't round it too much, but 2.8, 2.84, something like that. All right, that's it. Okay, I'm going to do one more topic. Again, you can practice some more of these. I'm going to talk about specific gravity before we move on too far. And I might even introduce this because specific gravity is so quick. Okay, so what is specific gravity? Actually, give me 1 second, guys. I got to just check something and then I'll be right back. Okay, sorry about that. I had another student talking to me in the other class, 1700, about coming to get their test, but it's not there. It's not outside my office yet. Okay, anyways, that has nothing to do with you. So specific gravity, you might have heard of this in physics or chemistry. In chemistry, it's very much, it's like the density basically. So you've probably heard of this before. The specific gravity, very much like the density of an object. I mean, it is the density of an object. It's the weight of a substance related to the weight of an equal volume of water. Okay, so I guess it's not exactly like density, but it's related to density is what I guess I should say. So specific gravity. In science and math, when you see the word specific, it's referring to a specific constant or a specific I'm going to say chemical, and in this case, it's water. The specific gravity is the ratio, it's the weight of a substance compared to the equal weight of water. And this number, the specific gravity, because it's related to water, this will actually tell you whether some chemicals are more or less dense than water. This means if the chemicals don't mix, it will tell you if it's going to float or sink on water. So I know you guys aren't in engineering, but my engineering students would look at specific gravity of hydrocarbons, of chemistry, or sorry, of carbon containing compounds to see, their densities and where they would be, if you mix them with other hydrocarbons and water and things like that. So kind of a useful number for engineering. You guys are going to use it just a little bit in this course. One thing you need to keep in mind is that the cool thing about water is the gravity, the density, the specific gravity of water is 1.000. So 1 milliliter of water is equal to 1 gram of water. So the density of water is 1. That's why water is such a cool chemical. The density of water is 1. So what does specific gravity mean? Well, the specific gravity is the ratio of that chemical's weight compared to water. So if the specific gravity of acetic acid, for example, is 1.05, it's a little bit more what we would say dense than water. Its specific gravity, its density is higher than water, and it's higher by a factor of 5%, which we'll talk about. You'll see this kind of come up a bit later. So again, the formula, this is this is given to you. It's the weight of your substance divided by the weight of an equal amount of water. Ammonium hydroxide, this is less dense than water. The specific gravity of ammonium hydroxide is 0.88. This means it's about 12% less dense than water. Okay, formic acid is much more dense than water, 1.22. Something like hydrobromic acid, 1.5. So it's significantly more dense than the water. The weight of hydrobromic acid would be way more than the weight of the same amount of water, by about 50%. Okay, sulfuric acid, the density of that would be about 84% more dense. Okay, so this again relates a lot to my engineering students, but we're just going to use it for some simple calculations here. And here's, I think you're given, I have your data sheet in front of me. This is equation 7, and this is equation 8 in your formula sheet. So these are given. That formula sheet I gave you during your test, you guys are going to use that for your final exam. I mean, it's the same thing, and it is on D2L if you lost it or didn't take a copy. Okay, so let's have a look. It's easier than it sounds, trust me. So example number 12. What is the volume of 492 grams of nitric acid with a specific gravity of 1.40? Okay, so we need to calculate this. What is the volume of 492 grams of nitric acid with a specific gravity of 1.4? So the weight of the liquid, oh, just hold on 1 second here. Sorry, 1 second. Okay, sorry about that. So we're looking for the volume of our liquid. Okay, and we have 492 grams of nitric acid, and the specific gravity is 1.40. Now, there's a little bit of thinking we have to do here. Volume of equal weight of water. Okay, well, I don't like equations that are that big. And then specific gravity of our liquid. Not of water, but of our liquid. Now, we can solve this right now, but you need to think about something. The first thing is saying, what is the volume of equal weight of water? So the question is, what is the volume of 490 grams of water? So what is the volume of 492 grams of water? That's where we need to start this question. So the volume of the liquid is equal to the volume of equal weight of water divided by the specific gravity of the liquid. Now, this is easier than it looks. The answer is 492 divided by 1.40. But how did I know that? How did I know that the volume of equal weight of water is 492? Well, remember, 1 gram of water equals 1 milliliter of water. That's the beauty of water. So if I'm telling you you have 492 grams of nitric acid, well, I'm looking for the volume of 492 grams of water, and that is 492 milliliters. Okay, I hope that makes sense. So again, the volume of water is, the density of water is 1 gram of that will equal 1 milliliter. So the volume of equal weight of water is the volume of 492 grams of water. Well, 492 grams of water is 492 milliliters. That's the beauty of water. So I'm going to take 492 and I'm going to divide it by 1.4 and I get my answer. 351 0.4 milliliters. You could just say 351 milliliters. Little bit confusing, a little bit challenging, but not too difficult. Okay, so I hope that's cool. Let's look at another one, and then I'll let you guys practice and we'll check the time. What is the weight of 3,620 milliliters of ethanol with a specific gravity of 0.78? Okay, so interesting, but we can do this. We're looking for the weight of the liquid, guy. And these formulas, by the way, guys, I am literally just writing these two formulas up here. In question number 1, I use formula 8. In question number 13, I'm using equation number 7. So this is where these equations come from. Okay, so weight of liquid is equal to the weight. I hate how these formulas are so big. Hey, it'd be nice if we could just use symbols, but this is better for you guys because when you're doing this on a test or something or your final, you don't have to memorize what symbols mean. Okay, so the weight of the liquid is the weight of the equal volume of water, that's very easy to do, times, I ran out of room, but this is times the specific gravity of the liquid. Okay, easy. So I'm doing the easy ones. I'm going to give you guys a harder one in a minute. So the weight of my liquid will be the weight of the equal volume of water. Now, this is the beautiful thing about water. Okay, my question is, in order to figure out the top part, what is the weight of 3,620 milliliters of water? Okay, so that will give me this right here. Well, 3,620 milliliters of water equals 3,620 grams of water. That's why water is so cool. I'll get a little chemistry or sciencey here. This does depend on temperature. So this number only works at a certain temperature. I think it's about 20 degrees. But anyways, we're not going to get into that. That's not what you need to be here for today. So I'm going to say 3,620 multiplied by, that's grams, multiplied by my specific gravity. There are no units for this. So I multiply that together and I'm done. 3,620 times 0.78 equals 2,000. Oops. That was a weird looking 2. 2,823.6 grams. One thing, I'm going to get you guys to practice this, but one thing I'll just comment on is, hold on, I just got to open up the comment part here so I can change the color of my pen. We're secretly doing percent calculations, but I'm not really telling you that. This is a percent. So what this means is the specific gravity of ethanol. This means that ethanol's weight is 78% the weight of water. So this number here means that ethanol is 78% by weight of water, of the same amount of water. So that's where that 0.78 comes in. What about this one? What does 1.4 mean? Well, this means that the volumes of water is 40% bigger than, or sorry, the volume of nitric acid. So volume of nitric acid is 140 times or 40% bigger than water. Or sorry, not volume, mass, or weight, I should say. Why did I change volume to weight just then? Because this was given in weight. So the weight of the nitric acid is that much bigger, which means my volume will be less. I don't know. I hope I'm not trying to confuse anybody, but I just wanted to explain to you that these are basically fancy percents. 1.4 would be 140%. This, or 40% bigger, this would be 78%, or 22% smaller. Anyways, I didn't mean to confuse you, but I just wanted to explain that. Oh, I guess that's it. Okay. So let's look at, let me show you one or two. Like, I'm pretty much done, but I'll just show you a couple of these. And then maybe tomorrow I'll ask you guys to try some and give me your answers. So give me, I don't know, 5, 10 minutes to maximum. And tomorrow I'll ask you guys to try these tonight, and we'll look at the answers tomorrow. So let's look at some examples here. Okay. So what if the percentage is given in weight? Okay, weight to weight percentage is a mixture of the weight of the solute divided by the weight of the solution. Same thing, no different. Did a student just, I thought I heard somebody's microphone. Okay, anyways, if you have a question, let me know. So percentage by weight, W over W, the weight of my medicine, or my, again, you could think of it like solute divided by the weight of the entire solution. So this is very useful when you're dealing with solids, you know, you're measuring a solid, or when you're given something like specific gravity, which we're going to, like, I'm going to kind of combine everything here and do one of these questions. The formula, which is obviously given to you, is the same as the previous formula. The previous formula, it was the volume over the volume. This will be weight over weight. So the weight will typically be in grams or kilograms. All right, let's look at some problems. It's easier than it looks, as always. I find sometimes, you know, the notes can be confusing, but the examples really clarify what it's about. So example 14, 300 grams of a mixture. Okay, so that's the total, right? I have 300 grams of the mixture. It contains 60 grams of the active ingredient, your medicine. So I have a solute, I have a solvent, sorry, not solute. I'm talking too fast. I have a solution. It's the entire mixture. So I have a 300 gram mixture or a 300 gram solution, and I'm looking at 60 grams of the active ingredient. So very simple, 60 over 300, multiply it by 100% to get your answer. So 60 over 300 would be 0.2. You would get a 20% solution. So 20% of the weight of your solution will be your active ingredient. By the way, if you're thinking, why would you ever need this? This is basically how some people might give you a recipe. So you're working at a pharmacy, you're working at a hospital, and they give you the recipe. They say that, you know, you need to make a medicine. Let's say that this medicine's a liquid, right? It's a syrup or something they would drink. And the doctor, or like the book, the training manual, whatever it is, says that this medicine needs to be a 20% solution. Now think about this. You're given a recipe and the medicine says you need 20% of the active ingredient, like whatever it is. Could be, you know, again, aspirin, paracetamol, acetaminophen, salicylic acid, I don't know. But the recipe just says 20%. And, you know, the hospital, the patient, they need 100 milliliters of this, or in this case, they need 100 grams. Well, how are you going to make that? How are you going to create this recipe? So it's kind of like a cookbook. You're following a ingredient list or a recipe to make something. If the patient needed 260 grams, how much would you need? How much medicine would you need? You know, it's a very easy calculation. You would just multiply it by 20% and you'd figure out how to make this. So again, I'm just trying to explain, you know, where you would ever need this in your real life, this is how you make recipes. I have a cookbook. It's called Modernist Cuisine. It's really cool. It's over by, I can see it over on my table over there. It's like a scientific, kind of like a cookbook for nerds, and all of the recipes are given as percentages. So this is kind of reminding me of that. It's a really good way to follow a recipe because you can scale the recipe, meaning you can create 50 grams for a patient, or you could create 120,000 grams for like in an industry. Anyways, let's look at example number 15. 30, oh, I hate this. So you guys, you can tell a math person did this. It's F, sorry. The American and North Americans use F, the British use PH. So whoever wrote this book was either British or just a math person. So anyways, we say F for sulfuric. 30 milliliters of sulfuric acid is dissolved in 100 milliliters of water. So sulfuric acid, we might need to calculate the specific gravity of this, but in this example, it's a very simple one. 30 milliliters of sulfuric acid is dissolved in 100 milliliters of water. Now, let's think about this. This is my active ingredient. So this I would call my solute. The 100 milliliters of water is my solvent. You'll notice nowhere here am I mentioning the total solution. What is the percent concentration? Well, here's your formula, but the solution itself, I need to add these masses together. Oops, not, 130 milliliters. Okay, so I divide that out, 30 milliliters divided by my total amount of solution, and I multiply it by 1. Guys, one thing you'll notice about this question is this is asking for volumes again. So this book is kind of all over the place, you know. I figured this would be a weight question, but nope, it's a volume question. Now, if I want to find the concentration in weight over weight, that's where specific gravity comes in or gets involved. And again, if you guys are confused, we're going to do some practice problems tomorrow. So what if I want to find the concentration in the weight ratio? Well, if I'm going to do this, I'm going to need to know the weight of the H2SO4 and the weight of the water. The weight of the water is very easy. 100 milliliters of water is equal to 100 grams. That's easy. But in order to find the weight of the weight of H2SO4, which is your sulfuric acid, I'm going to need the specific gravity of that. So the weight of H2SO4 is, I use my new specific gravity equation. It's the weight of the equal volume of water multiplied by the specific gravity of H2SO4. This is formula number, if you're looking at your formula sheet, this is formula number 7. Now, where did this come from? Not like where did the formula come from, but where did this come from? 184. This number you would find in a data booklet, or it would be given in the test question. So you'll notice from your data booklet, if you kept it from your test last week, I'm looking at it right now. You can hear the paper. It's not in that data booklet. So this number would have to be given to you. Okay, so the weight of the H2SO4, the sulfuric acid, would be the equal volume of water. So we're looking at 30 grams. Where do the 30 grams come from? Up in this question, 30 milliliters of sulfuric acid would be 30 grams of water. And I multiply it by the specific gravity of my new chemical, H2SO4, and I would get 52.5. So now I do the exact same calculation as I did before, 55.2. That's my new weight I just calculated, divided by the total. And I would get 35.6% by weight. Now you'll notice, guys, my numbers, let me use a different color. They're not the same number. So, and this is really important because if you were going to make the recipe using volumes, so volumes, you would use something like a graduated cylinder or a measuring cup. You would need to make this using the formula that you're going to need 23.1% volume. If you were going to use this using weigh scales, so you were going to make this solution using like a set of scales, when you measure weight, you would create it based on its specific gravity, so 35.6%. The recipes look different, but they're going to make the exact same chemical. It's really interesting how weight and volume can change a recipe. Which is, if I'm speaking about cooking, my friend made a bunch of cookies last night and gave me some. So I live kind of in a compound, and my friend was baking, made a bunch of cookies, brought them over. And a lot of times when you look at a recipe, again, if you don't bake, I apologize, but anybody here who's ever made like cookies or muffins or anything in their life, like in the kitchen, some recipes, especially American recipes, will give you volumes like quarts or milliliters even, or liters or cups, tablespoons. But you'll notice a lot of modern recipes use grams. And it's amazing that the difference between like a cup of, say, flour and then the weight of the flour. So it can really, really change your calculations. All right. Abdullah, I'm done. This isn't actually that long. Just for reference, I'm done now. But for reference, my MA1730, they have a 2-hour class, and we've been going about 1 hour 45 minutes every day. You guys, I typically go an hour to, today is 1 hour and 15. So I know it's a bit long, but that's it. We're done. So here's what I want you guys to try. Okay, so you can see this page here. I just explained, I hope I explained examples 14 and 15. I would like you guys to try some other ones tonight. And then when you come to class tomorrow morning, what time do I have you tomorrow? I have you tomorrow at 9:30. We'll start at 9:30. We won't start later. We'll start right at 9:30. We'll look at the answers to these. All right. So guys, that's it. I'm sorry I went long, everybody, but I hope it was somewhat interesting. That's it for me today. Lindsay wrote me a private message. Don't worry about disconnecting. Some of you might have problems with your Wi-Fi. I know I do. If I'm in a certain room in my apartment, I can't get Wi-Fi. So if you miss anything, just check out the YouTube. I'll have this up in maybe an hour or two. All right, guys, I'm done. Halas, we're finished. Give me a little bit of time to get your tests finished and put into the D2L PeopleSoft. Your tests will be up this afternoon. I can send you an email when your grades are uploaded. All right, that's it.